stoichiometry, if I was to spell that for you, we got S-T-O-I, stoichiometry. Okay, and we could break that down. Essentially, it's balancing our chemical equations. So clear that off. Okay, and so now if we look at this just a little bit, consider the case of 4 NH3 plus 5 O2 producing 6 H2O and 4 NO. What does that really mean? Well, what it means is this. Get my pen working here. That means NH3 is ammonia, so we have 4 ammonias. Okay, then we look at here, we have 5 oxygens. It's going to give us 6 waters and how many nitrogen monoxides? That's right, 4. Good job. Okay, chemists say in this case for every 4 moles, now we've talked about moles quite a bit, remember what the definition of a mole is. For 4 moles of for every 4 moles of ammonia or NH3, 5 moles of oxygen are required to produce 6 moles of water and 4 moles of nitrogen oxide. Okay. Now, I told you we'd talk about stoichiometry just a little bit. Stoichiometry here refers to the relative quantities of moles. Okay, so if I say quantities, okay, it also refers to calculations that make use of mole ratios. Now, when we're talking about mole ratios, remember what we talked about when we were balancing the equations. The law of conservation of mass, all of that, it has to be the same. Okay, we've gone over that pretty big in Unit 7, but now we're going to move on with Unit 8, and we're going to talk about it a little bit. Their balanced equations are like recipes. Okay. The recipe for a cheese sandwich would be 2 slices of bread plus 1 slice of cheese would produce 1 cheese sandwich, right? That's what we got here. We got our 2 breads, our 1, okay? So, if you were to predict how many cheese sandwiches, as defined by the picture to the right, that you can make if you have 6 pieces of bread and 4 slices of cheese, okay? So, I've got 6 pieces of bread. Well, I need 2 in order to make a sandwich, right? So 6 divided by 2 is 3. But I got 4 slices of cheese. But I only need 3 because the 3 sandwiches require 3 slices of cheese. So we wind up with 3 sandwiches is all we can make. And we're going to have a piece of cheese left over. Things off. Okay. Now, we're going to call it the Chemistry Cafe cook. Okay, he has a loaf which had 33 slices of bread and a package of cheese that has 15 slices. He is making sandwiches that have 2 pieces of both bread and cheese. How many sandwiches can he make? Okay, we need 2 cheeses, right? Or 2 loaf pieces of bread, so we're going to say our 33, and we're going to divide that by 2, and we're going to get 16 and a half. Right? Now, we can't make a half a sandwich. Well, we could, but we can't. Okay? So we could make up to 16 sandwiches just using the bread. Okay? Now I have 15 slices of cheese. How many do I need per sandwich? I need 2. So this time I'm going to divide by 2. That's going to give me 7 and a half. So how many sandwiches, or realistically, I only get 7 sandwiches out of that. So, when we're talking about making sure we have it right, we have to use the least one. That's what we call a limiting reactant. Okay, limiting reactant in this case was the cheese. All right, so let's move on to the next idea here. We have another kind of recipe, okay? We're going to be a tricycle factory. A tricycle factory. We're going to make tricycles, okay? We get a shipment of 400 seats and 600 wheels. How many tricycles can we make? All right, so I need 1 seat for a tricycle. And I need 3 wheels for a tricycle. Okay, so now I can make 400 tricycles with the seats I have, but can I make it with the number of wheels I have? So to determine this, I'm going to say I've got 600 wheels. Get my T-table. We talk about these a lot. How many wheels per trike? 3 wheels. We want to put the same unit on the bottom, and then we'll put the trike up here. Okay? So, we've got 600 wheels where one trike needs 3. So we take the 600, we divide by 3, and this says that we can only make 200 trikes. Is that more or less than the 400 seats? Okay, we got 400 seats. So we're going to use, excuse me, we're going to make 200 trikes. That's how we can do that. Okay, so, and we'll use up all of our wheels, but we'll also have 200 seats left. Does that make sense? The wheels now became what we called, remember that term, what limits it? That's right, a limiting reactant. The wheels are our limiting reactant. Okay, good. Now let's move on to the next idea. Okay.
Hey, Mr. Henderson. Let's look at example 1. First, we have this same old equation from before. 4 ammonias plus 5 oxygens makes 6 waters and 4 nitrogen monoxides. So that's our recipe. Our question says how many moles of water are produced if 0.176 moles of oxygen are used. So assuming that oxygen is the thing that runs out first, right, our limiting reagent, then we're going to start with what we're given, 0.7176 moles of oxygen. We're always going to start with the number they give us, right? And now how does oxygen relate to water? Water is our target. We want to get to moles of water, so we need to find the relationship between oxygen and water. So look to your recipe. I'm going to use 5 oxygens to make 6 waters. So that's our relationship. I'm going to put it into the T-table now. Notice that where I have moles of oxygen on top, I want to put moles of oxygen on the bottom. And I'm trying to turn it into moles of water, so that goes on top. Now I'm going to put the numbers in. This is called the mole ratio. So for every 5 moles of water, I keep saying that backwards. For every 5 moles of oxygen, I'm going to put 6 moles of water, because that's what we call the mole ratio from our balanced equation. You see, we couldn't solve these problems without a balanced equation. So now that I've got moles of oxygen to cancel, and I'm left with moles of water, then my problem's done. What do we do to solve this? The top times the top, and the bottom times the bottom. So let me get my calculator out, and we'll work it out. So I got this number 0.2112 moles of water. Now I'm going to look at my sig figs. I'm allowed to keep 3 of those digits, so let's round this to 0.211 moles of water. And you'll put a box around your answer, because that's the way I like it. Great, that's it. Your turn.
Okay, so here we have 4, 5, 6, and 4. Let's look at them. Okay, how many moles of nitrogen monoxide are produced in the reaction if we had 17 moles of water instead of 6? Okay, so what do you think we'll do? Okay, take what we're given, 17 moles, right? And we're going to divide by the ratio here. 4 nitrogen monoxides per 6 waters. Makes sense? For every 6 waters, I get 4 nitrogen monoxides. So, I got these 17 moles, and remember these are moles also. Okay, so we'll take 17 times 4. When you figure that out, you get 68. Let's say H2O. Okay, so we cross out our moles of water. So we get 68 moles of NO for every 6. Now, 68 divided by 6, that's going to give us, if I plug it into handy dandy calculator, I get 11 1/3 moles of nitrogen monoxide. Okay, because 11 times 6 is 66, remainder of 2, 2 divided by 6 is 1/3. Okay, so that's how many moles of nitrogen monoxide we could expect if we got exactly 17 moles of water. Okay, so let's clear this off, move to the next page.
Okay, let's look at example 3 then. So in this example, we're going to use the same equation, but now we're going to put a little twist on it, because instead of starting with moles, we're going to have grams. Actually, we're ending with grams, not starting with grams. So same equation, same recipe, only this time we're asked to find how many grams of water are produced if we start with 1.9 moles of ammonia combined with an excess of oxygen. So oxygen is not the limiting reagent here. It's the ammonia that runs out first. Great. So first, I start with moles of ammonia because that's what I'm given here, right? 1.9 moles of ammonia. And then my job is to change ammonia into water using my recipe. So my recipe says that for 4 moles of ammonia, I can make 6 moles of water. That's my mole ratio from the balanced equation. So notice in the T-table, ammonia is going to be diagonal. Where it was on top before, it goes on the bottom now so that I can cancel it out. And now I'm at moles of water, but the question asks for grams. Well, that's not a big deal because you guys have learned how to change grams to moles and moles to grams. So now I've got moles of water on top. I'm going to put 1 mole of water on the bottom, and how many grams are in 1 mole of water? You'll need your periodic table, or maybe by now you've memorized that hydrogen is 1 and oxygen is 16, so that's a total of 18 grams, 18.02 grams to be exact. So now let's do some math. You ready? Get your calculator handy. We're going to do 1.9 times 6 times 18.02. So on the top, I get 205.428. I'm not going to round until the end. Then we divide by what's on the bottom. So multiply across the bottom. Look, 4 times 1. I don't need a calculator for that part. Then we take the top divided by the bottom, and I got 51.357 grams of water. And let's round for 2 sig figs. So we'll just call that 51 grams of water. That's it. So put a box around your answer, because that's the way I like it. Okay, Mr. Henderson, you can take the next one.
Example. We got example 4. Same problem. 4 NH3 plus 5O2 produces 6 H2O and 4 NO. So now how many grams of oxygen are required to produce 0.3 moles of H2O? Okay, we know we have 0.3 moles of water. Okay, we're going to put this like this. We know we want to convert to oxygen, so we're going to put our oxygen on top, 5O2, and our water on bottom, 6H2O. Multiply that out, we get, 1.5. Our waters cancel out of O2 divided by 6. Okay, 1.5. So let's come over here. Let's say 1.5 divided by 6 is 0.2. Get 12 and 3, bring a 0 down, 0.25. So this is equal to 0.25 moles of O2. Now we ask that to convert into grams. So we take that 0.25 moles of O2, the molar mass of O2. Okay, we want grams. There's 2 of the 16, so it's 32 grams per 1 mole O2. Okay, now the moles of O2 cancel out. We got essentially 1/4 of 32. What 32 divided by 4 is what? That's right, 8 grams. So if I had 0.3 moles of water, I would need 8 grams of oxygen to create it. It was provided I had enough ammonia.
All right, then let's look at example 5. So if we still keep the same equation, we'll be consistent through all these examples, then we can talk about grams to grams, and we're going to have to use the mole ratio. So we have 4 ammonias combined with 5 oxygens to produce 6 waters and 4 nitrogen monoxides. Our target is grams of NO, and our starting point is grams of oxygen. So let's see, how do we relate grams to grams? Is that what a balanced equation tells us? Grams to grams? Not exactly. The balanced equation gives us a mole to mole ratio. So really, I'm going to have to go to moles. So that's all right. You know how to change grams to moles, right? So let's put grams across from one another. Grams of O2 will go on the bottom because we started with grams of O2 on the top. And that would be, for 2 atoms of oxygen, 32 grams equals 1 mole. Now, how do I relate the moles of oxygen to the moles of nitrogen monoxide? Look at your recipe. Here's oxygen, here's nitrogen monoxide. What numbers do you see there? Since moles of O2 is on top, I'm going to put moles of O2 on the bottom in my next step, and I'm changing it to moles of NO, so that goes up above. Now let's put the numbers in for our mole ratio. For oxygen, the number is 5 oxygens, so I put 5 oxygens here. And for NO, the number was 4 moles, so that's the number that goes with NO. Our final step is to change moles of NO into grams of NO, because that's what the question is asking for, grams. So if moles is on top in the step before, we got to put it on the bottom in the next step, because crisscross cancels, right? So NO, let's see, that's going to be 14 and 16 is 30 grams of NO for every mole. Now let's make sure that we got to the right place. Grams of oxygen canceled, moles of oxygen cancels, moles of NO cancels, and I'm left with grams of NO. Well, that's a good sign, because that's what the question is asking for. That's where I want to end up. And so I'm going to get my calculator, and we'll multiply 12 times 4 times 30. The top times the top times the top, all the way across. When you're dividing by what's on the bottom, remember to multiply across the bottom first. So I have 1440 on the top. And across the bottom, I have 32 times 5, which is 160. Now we'll do the top divided by the bottom. 1440 divided by 160, that's 9 grams of NO. And you should get numbers that are reasonable here. You should have something that matches up with 12 grams is what we started with, and so if you just had 1,440, that would be unreasonable. Don't forget to divide by what's on the bottom. And how many sig figs? Looks like I need 2, so we'll call this 9.0 grams of NO. That's it. So I have a tip for you. When you're solving problems like this, our saying is, when in doubt, go to moles. If you're not sure how to start a problem, go to moles. That'll get you halfway there. When in doubt, go to moles. You're going to hear me say that a lot. Alrighty, I think that's it. Back to you, Mr. Henderson.
Okay, so that kind of concludes podcast 8.1, the meaning of balanced equations. Now, stay tuned. Pretty soon we'll come up with some more podcasts. We'll put them out there for you. Remember, refer to these as you need to. They're always there for you to look at, refer to, do whatever you want. If you have any questions, ask me in class and we'll be good. All right, have a good day.